Hey guys, okay, so this would be our next video on rotations. This should be a little bit more straightforward because I don't have any questions, so I should be able to explain everything, completely together cohesively. So that's good. So first I'm going to kind of explain to you what a rotation is with a little drawing. So basically, we're going to be using 90-degree rotations as an example here. So we've got this x, right? Then we've got t of x, the transformation, and we've got y, vector y. So let's say that we rotate this counterclockwise for pi over 2. For people who do not know the unit circle, which might be a lot of y'all, that's 90 degrees. So we've got it rotated through 90 degrees, which means we go from here to here. We're going to use this to figure out, once again, the matrix that we would use for any rotation. So we've got our formal definition, which would be that the length of t of x equals the length of x, and the angle of t of x is greater than the angle of x by theta, right? We can see this here for, this drawing does not actually show it in 90 degrees, but it just shows it kind of for an arbitrary angle, but this is theta, right? So this is our formal definition for any rotation. So using trig, we can explain that t of x equals cosine theta of x plus sine theta of y. So why would this be? So if we've got cosine theta, if we're going to use, if we've got in the example of a 90-degree rotation, pi over 2, here's x, here's t of x, right? Well, if you're familiar with the unit circle, then what you're going to know is that if you've got something on this line, it's cosine of theta, that's going to be 1. Sine of theta is going to be 1 for this line. And this is only if you're familiar with the unit circle. If you're not familiar with the unit circle, you're kind of just going to have to take that at face value because that would be a long explanation. And you'll get to it at some point in pre-cal. So what we can do now, though, is just use kind of basic properties of algebra and extrapolate. And so we can say cosine of theta times x1, x2 plus sine theta times negative x2, x1. Or sorry, my bad. I meant to say y1, y2. What am I doing? This should say x1, y1, negative x2, y2. There we go. So once we've extrapolated this out, right, if this would be the rotation, then what we can do is we can very easily turn that into a matrix, because we can just say cosine theta times x1 minus sine theta times x2 cosine theta times y1 x1 plus cosine theta times x2. Oh no, this should be x1 negative x2 x1. Okay, sorry, I don't know why I went back and forth on that so much. But yes, so if we have this, we can very easily turn that into a simple matrix. And so once we figure that out, we obviously would want to pull the x out to get, the matrix rather than the systems of equations. So our matrix for any rotation would be cosine theta minus sine theta, sine theta, cosine theta. times x. Easy peasy. And then I will sum this up with a very quick theorem. This is, as you can tell, much shorter than the other one, the other ones. So if you've got theorem 2.2.3, rotations. So if we have a matrix of a counterclockwise rotation, because this is what it was for, was counterclockwise. In R2 through theta, matrix equals cosine theta minus sine theta, sine theta, cosine theta. And they point out that this would be of the form a negative b, b a, where a squared plus b squared equals 1. And of course, they point out that conversely, any matrix in this form is the rotation. So that's all we really need to know about rotations. Which means that since that was so short, I'm going to combine this with the next section, which is a rotation combined with a scaling. So if we have that, we've got a rotation combined with a scaling. We are going to kind of use an example here. So if we start out with this 0, 2, 1, 0. Clear line. And then, we multiply it by some matrix of the form here. Now, we're going to end up with AB negative 2B, 2A. And as you can see here, we have added in a scaling. Before I go on, I should probably briefly explain what a scaling is. The reason I didn't say this up front is because it's so simple. It will take about 3 seconds of your time. It's quite simple. The matrix for scaling would be for any positive k, the matrix of k0, 0k defines a scaling by k, because k0 times 0k times x would be equal to k0 times 0k times x1, x2, which would then equal kx1, kx2, which would then equal k times x1, x2, which would then equal k vector x. So that would be our matrix for any scaling. Did not take long. Now we're going to go back talking about rotations combined with scalings. So if we know this, we're dealing with two things. We're dealing with a polar angle, AB, and we're dealing with a scaling, B, of the vector. So, and a scaling of the vector. So what we need to think about here is that what is our scaling? It's going to be scaling by r, where r equals the square root of a squared plus b squared of the vector a, b. So that means that AB is going to equal r cosine of pi times r sine of theta, right? So, the way that we can think about this is if we've got R cosine R sine can equal A B. So, and by extension, it's going to equal negative BA because you just apply the same rule to the other half of the matrix. So if we're going to write out a really quick theorem understanding rotations and scaling, here's how we're going to deal with that. We've got theorem 2.2.4. So matrix is a form A, negative B, B, A, rotation, plus scaling. It specifically if R plus theta equals polar. If it's polar is the only time that we're actually going to talk about in this book. I actually don't know the other kind. So we don't even have to know what that means because the book doesn't include any other kind. So if we've got that, so yeah, they're saying if R plus theta is a polar coordinate of AB, then A negative B, B, A equals rotation through pi combined with scaling by R. In other words, you basically take your normal rotation matrix and then you multiply that by a scaling by whatever amount the R is. And remember, R is defined by that length, that distance formula. So that's when you have to deal with both of those things going on at once. I think that there's also time in this video to go ahead and do shears without cutting us off. And that will be the last of the new videos regarding new notes. The rest will just be problem set videos. So from the last lesson, we've got shears. The book explains the idea of a shear with the idea of a deck of cards. So they take, you've got like this plane, right? You've got a deck of cards. This is a very badly, well, I can do better than this. We can all strive to do better than that. So we've got a deck of cards. Okay. We've got a ruler kind of measuring, sticking out from the side. So if we were to take this from the side, what would be happening is that you've got the card, right? A vertical shear would make it be like that. Okay, so if we want to have the formula for a sheared vector, what we have to figure out here, so we've got vector x is x1, x2, and t of vector x is what we're trying to figure out. K is going to be the slope of the ruler after transformation, right? Because, it changed from here to here, right? So the way we can write this out is if we got t of vector x equals t of x1, x2, right? Pretty simple. So what we can do there is we can say that that's going to be x1 over kx1 plus x2. Now let's see, let's think about why that would be the case. So the reason why is because here the book gives this drawing. Where we've got x1, vector x, x2, and this here is the ruler. Then there's a sum transformation, and we end up with okay, so we end up with, we've got x here, we've got k of x1 here, which is our new slope, and x2 here. So if you want to try and find the transformation, we're going to have to add, we're going to have to add together, we've got the x1, right, up on the top, plus 0x2, because that's just this right here. But then we've got to deal with k times this new x1 plus x2. So that's going to lead us to having 1 times 0 k1 when we simplify this down times x1 y times x1 x2. So in other words, 1 0 k1 times vector x. So in other words, the matrix of a vertical shear is 1 0 k1. Now, if we had a horizontal shear, I mean, that would just be the same one, but the same idea, but instead of the deck of cards being shifted in that way, it would change to like that. And that matrix of a horizontal shear would equal 1k01. Yeah, so that's really all we need to know about shears. It's pretty simple. You just take this first value, right? And you change it here. And when you're trying to figure out, the transformation matrix, you take, your original x1, and then your new one, which would be here, right? And that's kind of how you form your matrix, and you can form the systems equation. You can use that to find your matrix, and then you kind of do the same thing for horizontal shears. So that is the basic ideas of this whole lesson. I'm going to do something that saved my life when I read the chapter, which is summarize. The book has this wonderful little summary in the back. And I want to end this video on it because at some point in the future, I'm probably going to have to look back through these videos to remember stuff. And knowing that I can come to the end of this video and just this long list is going to be really helpful. So we're going to start with scaling by k times I2 is going to equal k0, 0k. So these are the matrix. So the matrix for any scaling by k is k0, 0k. Orthogonal projection onto line L. That's U1 squared, U1, U2, U1, U2, U2 squared, where U1, U2 equals unit vector. Reflection of a line a reflection about a line is of the form AB, B negative A, where A squared plus B, where A equals 1. Rotation through angle theta. Cosine theta minus sine theta, sine theta cosine theta, or a negative b, b a, where a squared plus b squared equals 1. Rotation plus scalar, a negative b, b a, is, in other words, r times cosine theta minus sine theta cosine theta. Horizontal shear 1K 0 1. And finally, vertical shear 1 0 K 1. So that's everything that we just learned, basically summed up. The really important matrices that you're going to need to know for all of these transformations. So I hope that that is helpful. But yes, I'm going to come back with some basic stuff from the problem set that I did last week for the lesson on just like transformation.